Good afternoon. Today's topic is solving recurrence relation. In this topic, we will be seeing how can we solve recurrence relation. So we use a wide variety of recurrence relations and how is it that we are able to solve these recurrence relations. So the recurrence relations basically are also written as linear homogeneous recurrence relation, linear homogeneous recurrence relations, and these linear homogeneous recurrence relations have a degree k and they also have constant coefficients. So the linear homogeneous recurrence relations, we will see the general form of these linear homogeneous recurrence relations. To solve the recurrences, first we will see the definition. A linear homogeneous recurrence relation of a degree k with constant coefficient is a recurrence relation of the form an is equal to c1 into an minus 1 plus c2, we can have c2 an minus 2 and so on up to ck an minus k, where the ci's, that is the terms which have c1, c2 and ck, all of those are constants and they are all real numbers. Okay, they are real numbers, and whatever ck value we are taking, it should not be equal to 0. The solution that we want to find is uniquely determined if k initial conditions are provided, that is a0, a1 and so on up to ak minus 1 are provided, then we can find the solution for your linear homogeneous recurrence relation. So we already know what a recurrence relation is. Whenever we are supposed to find the next term by using the previous terms, that is known as a recurrence relation. Now, what do you mean by these terms, linear and homogeneous? So let's see that. First and foremost, what do you mean by linear? So linear is basically, if in the recurrence relation, the definition of recurrence relation, it can be known as linear if the right hand side, so the right hand side is a sum of the previous terms. So whenever we are doing the sum of previous terms, then that relation, that recurrence relation is known as the linear recurrence relation. Also, it should be a sum. Also, it can be multiplied by a function of n. That is, even it can be it can be multiplied by function of n. So you can have n into an minus 1 or plus n square into an minus 1. So some function of n can be multiplied to the previous term, then it can be linear. Okay. Now, when is it not linear? Whenever instead of the sum of the previous terms, we are taking the product or subtraction. So in this case, suppose if we are taking an is equal to a square n minus 2. Now in this case, this is not known as linear, for a square n minus 2. Then this is not a linear recurrence relation. Now, what do you mean by homogeneous? The recurrence relation is homogeneous because no terms occur that are not multiples of aj. Now, what do you mean by this? In this case, if we are writing, suppose the recurrence relation is being written as an is equal to an minus 1 plus 2. Now, this term 2, it is not in the form of an minus 1, n minus 2, an minus 3. It is simply a constant. So in this case, it is not known as homogeneous. Okay. So linear is basically when it is the sum of the previous terms, and homogeneous is basically when it is in the multiples of this an term, an minus 1, an minus 2 or an minus k. Okay. So let's see this in a bit of detail. So linear is right hand side is a sum of multiples of the previous term. So it should be the sum. If it is the product, then it cannot be linear. What about homogeneous? No terms that are not multiples of aj. So we cannot have an is equal to, we cannot have an is equal to an minus 1 plus 7. Some constant should not be there over here. it should always be in multiples of AJs. Now, what is the degree? So apart from that, one more thing we can see over here is this, we can have a constant. So this C1, C2, Ck are all constants. The coefficient, so the coefficient of an minus 1 is C1, the coefficient of an minus k is Ck. So the coefficient of the terms of the sequence are all constants rather than functions. So they are not functions like n square, n, etc. They are all constants that depend on n value. Now, apart from that, we have degree. So the degree is k because en is expressed in the previous k term. So in this problem, the degree is k. So why is it k? Because we are using k previous terms to express our an. Okay. So for specifically this problem, the degree is k. If we change our problem, if we change our example, the degree will also change. Now the next thing is, let's see a few examples before going for solving the problem. So let's see some basic examples. Now over here, suppose we have our principal interest problem, compound interest problem actually. The solution, if you remember, was Pn is equal to 1.11 into Pn minus 1. The compound interest was 11%, I believe, for a sum of principal amount of 10,000. So for that problem, if you refer to the earlier class, you will see that the solution was Pn is equal to 1.11 into Pn minus 1.11 into Pn minus 1. Now, is this a linear, homogeneous recurrence relation? Okay. So it is a recurrence relation because Pn is being expressed in Pn minus 1 term. So this part, it can be said as, yes, it is a recurrence relation. But what about linear and homogeneous? So for this, let's check whether, what is the condition of linear if our right hand side is the sum of the previous terms. So over here, we only have one single term and it is obviously written along with a coefficient. So it is linear. Okay. So the linear condition is satisfied. What about homogeneous? Is it homogeneous? Yes, it is homogeneous. Why? Because there is no number or constant being added. That is, we have our right hand side in multiples of Pn only. We have Pn, over here we have Pn minus 1. So it is also homogeneous. Now, what is the degree? One second. So what is the degree of this recurrence relation? So the degree is, what did I say in the actual, the general formula we had was an is equal to C1 an minus 1 plus C2 an minus 2 plus and so on Ck an minus k. In this problem, the degree was k. Whatever is the last term, that is the degree. So over here, we have Pn minus 1, so the degree will be 1. Okay, so the degree is 1. Now let's take another example. The another example is our Fibonacci series. Fn is equal to Fn minus 1 plus Fn minus 2. Now, is it linear, homogeneous recurrence relation? We already know that it is a recurrence relation because we are expressing the next term in the sum of previous two terms. Is it linear? Yes, because we are not using multiplication, we are using the sum. That is, the right hand side is the sum of the previous terms of the sequence, each multiplied by a function of n. So we are being multiplied, this number is being multiplied with the constant 1. So it is fine, it is linear. What about homogeneous? So what about homogeneous? Yes, it is homogeneous because we don't have any constant being added. So it is homogeneous. Now what is the degree? So we have two terms over here, n minus 1 and n minus 2. What will be the degree? The degree will be the last term. So the degree of this problem is 2. Okay, so this is another example. Apart from that, let's see this example. An is equal to an minus 5. So is it a linear homogeneous recurrence relation? Obviously yes, because we are not multiplying or adding anything to it. So it is a linear homogeneous recurrence relation. but what is the degree of this problem? So the degree of this problem is 5, because the degree will be whatever the number an minus k. Since we have only one term over here and we are using n minus 5, so the degree is 5. Now, what about the few examples where I will explain you why is it either not linear or not homogeneous. So in this case, suppose if we take the example an is equal to an minus 1 plus a square n minus 2. Now if you notice, we have to find for linear homogeneous recurrence relation. It is a recurrence relation, yes, agreed, because we are using the previous two terms. Is it homogeneous? Yes, it can be homogeneous. But what about the linear condition? In the case of linear, what is the condition? What is the statement for the definition of linear? The recurrence relation is in the definition is linear if the right hand side is the sum of previous terms. But in this case, a square, it is not the sum. We are multiplying an minus 2 twice. That is the reason we have a square. And this is not linear. Okay. So this is not a linear homogeneous recurrence relation. It is a recurrence relation, but it is not linear. Similarly, let's take another example. So the example is our Hanoi-Towers relation Hn is equal to 2Hn minus 1 plus 1. Here we are adding the constant 1. So obviously directly we can identify that it is not homogeneous, because we are not using the multiples of Hn minus 1, Hn minus 2. We are not using that. We have added a constant. So the recurrence relation what we got was 2Hn minus 1 plus 1. So this is not homogeneous. Similarly, if we have another example, Bn is equal to n into Bn minus 1. Oh, in this case, we don't have a constant coefficient. Every time our coefficient should be constant and a real number. But in this case, our coefficient is not constant. It is expressed in terms of n. So this recurrence relation does not have a constant coefficient. Now, one last thing to be understood is, why do we study linear homogeneous recurrence relation? The reason we study linear homogeneous recurrence relation is for two reasons. So the first one is, they often occur in modeling of problems. Okay, so whenever we are supposed to solve problems, so they often occur in modeling of problems. Also, the second reason is they can be solved systematically. So systematically they can be solved in some order. So that is the reason we solve linear homogeneous recurrence relations with constant coefficients. So first and foremost, the basic approach to solve them is we have to look for the solutions of the form an is equal to r power n, where r is a constant. Okay, so an is equal to r power n is a solution of the recurrence relation. If suppose our recurrence relation is given as follows, an is equal to c1 an minus 1 plus c2 an minus 2 plus and so on ck an minus k, and then our solution will be given in the form if and only if instead of an we will replace it with r power n is equal to c1. Instead of this an minus 1, I'll replace it with r power n minus 1 plus c2 r power n minus 2 plus and so on ck r power n minus k. So each and every time we are replacing our a term with the r term in terms of exponents. Okay. So now when both sides of this equation are divided by r power n minus k, we will get r power k minus, so let me just explain it by using the whiteboard. So if I am dividing both sides of the equation, so this equation r power n is equal to c1 r power n minus 1 plus c2 r power n minus 2 plus and so on ck r power n minus k. Now for this equation I am dividing it on both sides by r power n minus k. When I divide r power n divided with r power n minus k on both the sides. Here I'll get r power n by r. So let me just write it. A power m by a power n will give me a power m minus n. So r power n by r power n minus k will simply give me r power k is equal to C1 r power k minus 1, and each time will get cancelled, plus C2 r power k minus 2, plus and so on, Ck minus 1 r. So I am writing the previous term. So over here, I'll write it in this case also. So on. The term before this will be Ck minus 1 r power n minus k minus 1. Okay. So n minus k minus 1, or we can even write it as, yeah, n minus k minus 1. So when we divide it by r power n minus k plus 1 actually, so it will be C of k minus 1, C of k minus 1 into r plus C power k. So r power n minus k and r power n minus k will get cancelled. Now all these terms on this side have to be moved to the left side. So RHS is being completely moved to the left hand side. So we will get r power k minus C1 r power k minus 1 plus C2 r power k minus 2. Actually here it will be minus, and then again all the terms will become negative since we are moving it to the other side, minus c power minus ck, the constant ck is equal to 0. So the sequence an with an is equal to r power n is a solution if and only if r is a solution of this last equation. Okay, and this characteristic equation, this equation is known as the characteristic equation. Characteristic equation of the recurrence relation given. As we will see, these recurrence relations can be, and the solution for this characteristic equation. So the solution of the characteristic equation are called the characteristic roots of the equation. So when we find the roots of the equation, those are called as the characteristic roots of the recurrence relation. Okay, so we will see that the characteristic roots can be used to give explicit formulas. So we will find some formulas. So the first is the theorem based on this characteristic roots. So this is the first theorem or the first formula based on the characteristic roots. So what is the theorem 1? So let C1 and C2 be the real numbers, and suppose our equation, so C1 and C2 are constants, and our characteristic equation is in the form r square minus C1r minus C2 is equal to 0. This is the characteristic equation that we have got, and this equation has two distinct roots. It has two distinct roots. What are the roots? They are denoted with R1 and R2. Then the sequence, our recurrence relation sequence an is a solution of the recurrence relation an. So what is our recurrence relation? It will be in this form. If we have two roots, then we will get two previous terms. So C1 an minus 1 plus C2 an minus 2. If and only if, so the solution for this sequence is given as an is equal to alpha r1 power n plus beta r2 power n, for n is equal to 0, 1, 2 and so on, where these alpha and beta, are constant. Okay, once again let me summarize it for you. So over here we have the recurrence relation or the sequence an. Okay, an is given as c1 an minus 1 plus c2 an minus 2. Now whenever we have if the next term in terms of the two previous terms, then we will get the characteristic equation also a quadratic equation, that is r square minus c1r plus minus c2 is equal to 0. What are c1 and c2? C1 and c2 are two real numbers which are constants. Now when it is of this form, when we get a characteristic equation of this form, and then for this characteristic equation, these are the characteristic roots. Okay, the roots for this quadratic equation are r1 and r2. Then the solution for your problem an will be given as an is equal to alpha r1 power n plus beta r2 power n. In the textbook, we will have alpha 1 and alpha 2. So alpha and beta are anyway constant. So you can take any of the constants. You can even take x, y, y, z, p, q. It does not matter because these are constants. Now, based on this, let's solve a problem. The question is, what is the solution of the recurrence relation what is the solution of the recurrence relation an is equal to an minus 1 plus 2an minus 2 with, we will also be given initial conditions. So with a0 is equal to 2 and a1 is equal to 7. Now we have been given the recurrence relation as this: an is equal to an minus 1 plus 2an minus 2, and a0 and a1 are also given. So first and foremost, we have to convert this recurrence relation into what kind of equation? We have to convert it into characteristic equation. So to convert it into characteristic equation, replace an, let me write this step, replace an with r power n, and subsequently an minus 1 with r power n minus 1 and an minus 2 with r power n minus 2. So in this case, and also move all the right hand side terms to the left hand side. We will get r power n minus r power n minus 1 minus 2r power n minus 2 is equal to 0. Now, what is the next step? The next step is divide this equation with r power n minus 2. When you divide this equation with r power n minus 2, r power n by r power n minus 2, let me write it over here. A power m by n is equal to a power m minus n. R power n minus of plus 2, so we will get r square. So this is written as r square minus r minus 2 is equal to 0. Now, after that, here we are supposed to find the roots. So this equation that we have got is the characteristic equation. This is the characteristic equation. Now we are supposed to find the characteristic roots. So what are the roots of the equation? It can be written as r plus 1 into r minus 2 is equal to 0. Okay. So, or you can even use the formula which is minus b plus or minus b square minus 4ac by 2a. Either this formula or you can directly factorize it. Now, what are the values of r1 and r2? The values of r1 and r2 are as follows. r1 will be equal to minus 1 and r2 will be equal to 2. Now, the sequence an is a solution to the recurrence relation if and only if we get it in this form. So the formula, if you remember from the previous theorem, was an is equal to alpha r1 power n plus beta r2 power n. So let me write it over here. an is equal to alpha r1 power n plus beta r2 power n. Now, instead of r1 and r2, we will substitute the values of the R1 and R2. So minus 1 power n plus beta 2 power n. All right. So now this is your equation 1. Okay. This is the general solution and this is the equation. And what are these alpha and beta? They are some constants for some constants alpha and beta. Now after that, once we have this, we have been given the initial condition. What were the initial condition? A0 was 2 and A1 was 7. So let's substitute the values of the initial condition in our equation that we have written as equation 1. So this was our equation 1 from our earlier slide. So over here, this is our equation 1. So in this equation, substitute n is equal to 0 and n is equal to 1. So when we substitute n is equal to 0, what is the value of A0? It is 2. 2 is equal to alpha 1 into 2 power 0. Oh, I'm sorry, let me just replace it with alpha and beta, since I usually use. So an is equal to, let me write it from here, alpha into minus 1 power n plus beta into 2 power n. Now substitute n is equal to 0 and n is equal to 1. So A0 will be alpha into minus 1 power 0 plus beta into 2 power 0, and A1 will be alpha into minus 1 power 1 plus beta into 2 power 1. So this will give us the equations. What is the value of A0? 2 is equal to alpha plus beta, since minus 1 power 0 and 2 power 0 is 1, and A1 is given as 7. 7 is equal to minus alpha plus 2 beta. Okay. Now when we solve these two equations, these are equations 2 and 3, solve equations 2 and 3 to find the value of alpha and beta. Solve 2 and 3. So when we solve 2 and 3, we will get alpha is equal to, so alpha is equal to minus 1 and beta is equal to 3, I believe. Let's solve it. So over here, alpha and minus alpha will get cancelled. 3 beta is equal to 9. So beta will be equal to 3. Okay, so and we can substitute over in this equation and we will get alpha is equal to minus 1. Now, what is the solution to the recurrence relation? You have to substitute the values of alpha and beta in this equation. So let me write it. An is equal to alpha into minus 1 power n. So instead of alpha, we are supposed to write the value of alpha. So over here, we will write minus 1 into minus 1 power n plus beta is 3 into 2 power n. So minus 1 into minus 1 power n, or even we can write it as an is equal to 3 into 2 power n minus of minus 1 whole power n. So let me just write it clearly over here. The final solution to the recurrence relation, with the initial condition given is an is equal to 3 into 2 power n minus 1 power n. So this is your solution to the recurrence relation. Let's look at the theorem a bit more clearly. So C1 and C2 are the real numbers, and we have the equation, characteristic equation, as r square minus C1r minus C2 is equal to 0, where the roots are r1 and r2. Then the sequence that we have an, it is the solution of the recurrence relation. An is equal to C1 an minus 1. So this is the recurrence relation that is defined. For that, the solution is given as an is equal to, this is alpha r1 power n plus beta r2 power n. N should be always greater than or equal to 0, or even you can write it as n is equal to 0, 1, 2 and so on. And a1 and a2 are constants. I'm sorry, here it will be alpha and beta are constants. Now based on this, the example that I've already solved, here it is a bit clearer. So the recurrence relation is given as follows: an is equal to an minus 1 plus 2an minus 2. And these are the initial conditions. Initial condition is a0 is equal to 2 and a1 is equal to 7. Then we have, what we do generally is we replace an with r power n. So we have replaced r power n is equal to r power n minus 1 plus 2r n per n minus 2. Now to this equation, we divide it by the smallest r power term, so r power n minus 2, and then we get the resulting equation as r square is equal to r plus 2, which can be written as r square minus r minus 2 is equal to 0. Now using the theorem, we know that what are our C1 and C2 are the constants. They are 1 and 2. This is not really important. We just need to find the characteristic equation which is given over here. Now for this equation, you have to find the roots of this equation. What is R1 and what is R2? So R1 and R2 are as follows. So anyway, you can take R1 as 2 or you can take it as minus 1. That is, both of the numbers can be taken vice versa also. Now after that, we have to use our theorem. What was the theorem? An is equal to alpha r1 power n plus beta r2 power n. This is very important. When is this? When the roots are real and distinct. Roots are real and also they are distinct. In that case, we have this an is equal to alpha into 2 power n plus beta into minus 1 power n. What is this 2 power n? This is here r1 and this is here r2. Alright. Now after that, to find a1 and to find here alpha and beta, solve the equation for the initial conditions a0 and a1. So we have a0 and a1 already. a0 is given as 2, a1 is given as 7. So basically in our this equation, which is our equation 1, what we do is we substitute n is equal to 0, substitute n is equal to 0 and n is equal to 1. So once we substitute n is equal to 0, we get this equation, which is alpha plus beta is equal to 2. And when we substitute n is equal to 1, we get 2 alpha minus beta is equal to 7. So in the earlier, I have taken 2 as my r2 and minus 1 is r1. You can take any of it, it is okay, alright. Similarly, we get these pair of equations. So here, instead of alpha being minus 1, we got alpha is equal to 3. Both the solutions are correct. Understand that both the solutions are correct. Both of them are constants and we don't need to worry whether alpha is 3 or beta is 3. Both of them are correct. So alpha is 3 and beta is minus 1. So to find the solution, we get an is equal to 3 into 2 power n minus 1 power n. So this is the final solution. We substitute the alpha and beta values in this equation and we are getting our final solution. Alright. So this concludes the first approach where the roots are real and distinct. So this is your theorem 1. Similarly, we will have, with 2 roots, we will have one more theorem. So we will see that in the next lecture.